How engineers keep tall buildings from swaying. Imagine standing near the top of a skyscraper hundreds of meters above the ground. The building looks perfectly still, but high above the street, it may be moving. Wind pushes it one way, then back again. And during an earthquake, the ground itself can suddenly move beneath it. So how can a structure this tall remain stable without simply fighting every movement? Let's find out. The building that moves. A skyscraper can weigh tens of thousands of tons. Yet despite all that weight, its upper floors can move slightly when strong winds pass around the building. And surprisingly, that's not necessarily a problem. In fact, engineers expect tall buildings to move. Picture a very tall ruler. If you push the top gently, it bends and moves much more than the bottom. A skyscraper behaves in a similar way. The taller the building becomes, the more important movement becomes. But here's the real challenge. Engineers don't simply need to stop the building from moving. They need to control how it moves. Why? Because completely rigid structures can actually experience enormous forces. So the goal isn't to make a skyscraper frozen in place. The goal is to make its movement predictable, controlled, and comfortable. And that's where the hidden engineering begins. Why wind becomes a problem. Now imagine a strong wind hitting a skyscraper. The wind doesn't just push once. It constantly changes direction and speed. The building responds by moving slightly. Then it moves back. And then the cycle can repeat. At street level, you might never notice. But hundreds of meters higher, even small movements can become noticeable. This creates two different problems. First, the structure must remain strong enough to handle the forces. Second, people inside shouldn't feel like they're standing on a giant swinging platform. Here's the clever part. Engineers shape the building itself to work with these forces. Look closely at many modern skyscrapers. Their shapes aren't always chosen simply for appearance. Some buildings gradually become narrower as they rise. Others use setbacks, rounded corners, or carefully arranged sections. Why? Because changing the shape can disturb the airflow around the building. Instead of allowing powerful wind forces to build up in a repeating pattern, the design can help break that pattern apart. But even the best shape can't eliminate movement completely. So engineers need another solution. The structure inside. Now let's remove the glass exterior and look inside. A skyscraper is not just a giant stack of floors. Deep inside is a carefully engineered structural system. Depending on the building, this can include massive columns, beams, reinforced concrete cores, steel frames, and diagonal bracing. These systems work together to carry the building's weight and resist sideways forces. Imagine pushing a stack of cards sideways. It can easily deform. Now imagine connecting those cards with strong diagonal supports. The entire structure becomes much harder to distort. That's the basic idea behind many structural systems. But engineers still face a problem. The stronger the structure becomes, the more force it may have to absorb. So instead of trying to resist everything with strength alone, engineers can also use something more subtle. Damping. Think of a car driving over a rough road. Its suspension allows movement, but shock absorbers prevent the car from bouncing endlessly. Buildings can use a similar principle. And this is where things get really interesting. The hidden dampers. Now zoom inside the upper levels of a skyscraper. In some buildings, engineers install large damping systems designed to reduce unwanted movement. One famous approach is a tuned mass damper. Imagine placing a very large mass inside the upper part of a building. It can move in a controlled way as the building moves. When the skyscraper begins moving in one direction, the mass responds in a carefully calculated way. Its movement helps counter part of the building's motion. It is almost like having a giant mechanical counterweight quietly working inside the skyscraper. And the remarkable part is that people walking through the building may never know it's there. But wind isn't the only challenge. Because now we have to take the building underground. When the ground moves, an earthquake creates a completely different problem. During strong ground motion, the foundation moves with the earth. But the upper part of the building has mass. And mass doesn't instantly change direction. That difference creates forces throughout the structure. Picture a passenger standing inside a moving bus. If the bus suddenly moves forward, the person's body tends to lag behind. A tall building experiences a related effect during rapid ground movement. The foundation moves. The structure above responds. And engineers have to control the resulting forces and movement. This is why earthquake-resistant buildings can use specially designed structural frames, reinforced cores, bracing systems, energy-dissipating devices, and in some designs, base isolation. Base isolation changes the connection between the building and the moving ground. Instead of forcing the entire structure to follow every sharp movement directly, specially designed isolation systems can allow controlled movement at the base. But here's something important. No engineering system can promise that a building will never move during an earthquake. Movement is expected. The engineering goal is to manage it and prevent uncontrolled structural damage. The complete system. Now let's put everything together. Start underground. The foundation transfers the building's enormous weight into the ground while helping the structure respond to the conditions of the site. Move upward. The core, columns, beams, and bracing create the main structural skeleton. Now add the building's shape. Its geometry can influence how wind interacts with the structure. Then add damping systems where appropriate. These can reduce unwanted vibrations and improve comfort. And in earthquake-prone regions, engineers may add specialized systems designed to handle seismic forces. Notice something important. There isn't one magical component keeping a skyscraper stable. It's an entire system. The foundation, the structural frame, the building's shape, the materials, the connections, the damping systems, and the engineering calculations behind all of them. Each part has a job, and each part must work with the others. The engineering trick. Now return to that skyscraper standing in the wind. From the street, it looks completely motionless. But high above, it may be moving slightly. And that's actually evidence that the engineering is doing its job. A good skyscraper doesn't need to behave like a stone block. It needs to behave more like a carefully controlled system. Flexible where flexibility is useful. Strong where strength is necessary. And damped where movement needs to be reduced. That is the real engineering trick. Engineers don't always defeat nature by making structures completely rigid. Sometimes they control natural forces by allowing the structure to respond in a carefully designed way. Great engineering isn't always about stopping movement. Sometimes, it's about understanding movement so well that you can control it.